At midday in the desert, the ground can become hot enough to burn exposed skin. The air is dry. Shade is scarce. And every breath, movement, and drop of sweat can remove water that may not be replaced for days. For most large mammals, extreme heat creates an urgent problem. Their bodies must remain within a relatively narrow temperature range. When internal heat rises, they begin spending water to remove it. They sweat. They pant. And as water evaporates, the body cools. This works well when another drink is nearby. In the desert, it can become a dangerous trade. Every drop used for cooling is a drop that can no longer support circulation, digestion, or the normal function of organs. Camels face the same laws of biology. They are not immune to thirst. They do not store drinking water inside their humps. And they cannot survive indefinitely without replacing what they lose. But their bodies are extraordinarily good at delaying that loss. A camel can tolerate levels of dehydration that would place many other mammals in severe danger. In classic desert experiments, camels endured water losses approaching 30% of their body weight. Their survival depended on two broad advantages. They could tolerate their bodies becoming unusually dehydrated, and they could reduce the rate at which their remaining water disappeared. The most surprising part of this strategy begins with heat. A dehydrated camel does not always defend one perfectly constant internal temperature. Instead, it can allow its body to become warmer during the day. That may sound dangerous. But in the desert, controlled heating can save an extraordinary amount of water. Imagine trying to keep a building at exactly the same temperature while the desert outside grows hotter every hour. The cooling system would need to run constantly. A camel uses a different strategy. When water is limited, its body temperature can fall during the cool night and rise gradually as the day becomes hotter. Instead of immediately removing all incoming heat through evaporation, the camel temporarily stores part of that heat inside its body. Its tissues act like a thermal battery. During the hottest hours, the camel becomes warmer. But because its body temperature is now closer to the temperature of the surrounding air, heat enters the animal more slowly. The camel can postpone some of its sweating. Then night arrives. The desert air cools. The stored heat can escape into the environment without requiring the same loss of water. In dehydrated camels, the difference between the coolest and warmest body temperatures over one day can exceed 6 degrees Celsius. That is a much larger daily fluctuation than most humans could safely tolerate. The camel is not simply overheating without control. The variation is part of a regulated water-saving strategy. Its coat adds another layer of protection. Thick fur may seem like a disadvantage in a hot desert. But it forms a barrier between the scorching environment and the skin. Sunlight heats the outer coat while less heat reaches the body underneath. Experiments found that removing the coat increased the camel's water expenditure. Without that insulation, more environmental heat reached the animal and more evaporative cooling became necessary. The camel therefore uses two apparently contradictory adaptations. It carries a thick coat in extreme heat, and it allows its internal temperature to rise. Together, these reduce the amount of water that must be sacrificed during the hottest part of the day. The camel does not defeat heat by remaining permanently cool. It survives by deciding when cooling is worth the cost. Allowing body temperature to rise only delays the need for cooling. To survive prolonged dehydration, a camel must also protect water throughout the rest of its body. Its strategy is not based on one magical organ. It is a collection of small savings operating at the same time. The kidneys reduce the volume of water lost in urine. The digestive system removes much of the remaining moisture from waste. And as dehydration becomes more severe, the animal limits unnecessary evaporative loss. In classic experiments, dehydrated camels produce remarkably small volumes of concentrated urine. Their feces also contained little water. These savings matter because desert survival is a problem of accumulation. A small loss from one process may seem unimportant. But repeated every hour, over many days, it can determine whether the animal reaches the next water source. The camel's hump also contributes, but not in the way many people imagine. It does not function as a water tank. The hump primarily stores fat. That fat is an energy reserve that can support the animal when food becomes scarce. Keeping most of this fat concentrated in one region may also avoid placing a thick insulating layer over the entire body. The camel still needs water. It still loses water through breathing, waste, and cooling. And factors such as workload, temperature, diet, age, and health affect how long it can continue. A resting camel protected by its coat can endure conditions that a working or unhealthy animal may not. In one landmark summer experiment, a camel eating dry food was kept without drinking for 17 days. That was a controlled observation, not a universal deadline for every camel. The important lesson is not a precise number. It is the way multiple mechanisms cooperate. Less urine, drier waste, delayed sweating, stored fat, reduced heat gain, and an unusual tolerance for the gradual concentration of the body's remaining fluids. A camel survives dehydration by treating every possible water loss as an expense that must be justified. Eventually, conservation is no longer enough. The camel reaches water. And now it faces a very different physiological challenge. After days of dehydration, its body fluids have become concentrated. Its circulation has adapted to a reduced volume of water. Suddenly drinking an enormous amount could create rapid changes throughout the bloodstream. For many mammals, extreme dehydration followed by uncontrolled rehydration can damage cells and disrupt circulation. Camels are unusually well equipped for the transition. They can drink large quantities in a short period and begin restoring the water they have lost. Early observations described severely dehydrated camels replacing approximately 30 gallons within about 10 minutes. Later experiments confirmed that water is absorbed rapidly, although the redistribution and stabilization of body fluids continue for hours. Camel red blood cells are especially distinctive. Unlike the familiar round red cells of humans, camel cells are elliptical. Their membranes and osmotic behavior allowed the blood to remain functional through major changes in hydration. Research found that the red cells of dehydrated camels became more resistant to rupture in dilute solutions. Other experiments observed that their overall elliptical form remained stable during dehydration and rewatering. No single feature makes rapid rehydration completely risk-free. The digestive system, circulation, kidneys, tissues, and blood cells must all manage the returning water. But together they allow the animal to move from severe dehydration toward recovery with remarkable speed. This completes the camel's survival cycle. During the day, it stores heat instead of immediately spending water. Its coat reduces heat entering the body. Its kidneys and digestive system restrict unnecessary losses. Its tissues tolerate extensive dehydration. And when water finally appears, its circulation can manage rapid replacement. The hump is not the real secret. There is no hidden tank. The true adaptation is the entire animal. A camel survives the desert because its body can change the rules that most mammals are forced to follow. It can become hotter, drier, and more concentrated. Then, when the opportunity arrives, it can reverse the process and begin again.